So, have you ever wondered why, when blacksmiths they work with steel and they heat up their swords to punch them and to make them stronger, why do they glow? So the fact is, when the atoms they are agitated, they they will basically shoot off electromagnetic radiation. So this redness that we see in the steel here, it's basically our way, it's the way of our senses to realize that there is some chemical reaction happening. So as we saw last lesson, different wavelengths will interfere with the electrons in the layers, in the orbits around the nuclei, and it will basically either absorb photons and then become more energetic, or emit photons and become less energetic. So if we are actually able to observe light through some of those materials, so let me show you the apparatus, the practical apparatus which was designed now around 100 years ago. So what is done here? I've got some white light, and this white light will go through the substance that we want to observe, right? And what's going to happen is that this substance is going to absorb some of those wavelengths. White light is composed of basically all colors, right, that we see. So this substance is going to absorb a few of those wavelengths, and when we observe in a microscope or a sensor or anything, any visual capacity that we have, for example, we might make some graph like this one on a computer, a diagram like this one, and if you observe, if you get this white light which has been through the gas and you diffract it, so just like the cover of the album, right? You have light coming in and then it diffracts, right? And then you see all bands of color, right? Different frequencies. And then basically you realize, oh, it's missing some frequencies here. And what has happened is that this substance has absorbed some of those wavelengths. So what we observe is those black lines here, which, well, they are basically, black here is the absence of that wavelength, absence of color. So when we spread this light around, and we can see it here, right, we can see that it's missing some wavelengths, and by analyzing those wavelengths we have realized that different substances, they have different pictures, right? We can even call this like a fingerprint, because each substance will have a different absorption spectrum. This is what we call the absorption spectrum, right? If you look here on the top, those are the wavelengths which were absorbed. Those were the ones which went through. So this is what we call emission and absorption spectrum. This is specific for hydrogen, and the funny thing is, each substance will have a different one. So you can use this technology and this technique to detect what kind of chemical substances do you have in planets, stars and galaxies far, far away, just by observing their emission spectra. And this is consistent. You can really find out, oh, it's like a signature, it's like a fingerprint. And well, this is the absorption. So this is when we shine light through our substance and it absorbs some of those wavelengths. And in this case here, it's, if we were to analyze what light was produced, what kind of electromagnetic radiation was produced by our substance, those would be the wavelengths that would be possible. And those are basically connected to our energy levels that we saw in the last lesson, right? They have to do with the quanta, the smallest amount of energy quantity that we have in the universe, and basically each substance will absorb, will have different energy levels, therefore their signatures are going to be different. Oh, and just as a side note, it's actually more than 200 years ago, not 100. So yeah, it's quite old technology, but we still use it nowadays, and we use it more than ever to detect, for example, the composition and the chemical composition of things which are too far that we cannot get there, or we might not even ever be able to get there. Alright, so a few questions for us to work with. Now, the first one here, remember that you can always pause and try it yourself. So the element helium was first identified from the absorption spectrum of the Sun. Number one, explain what is meant by the term absorption spectrum. And number two, outline how this spectrum may be experimentally observed. So, an absorption spectrum consists of a continuous spectrum that has a number of absorption lines crossing it, the lines that we saw in the previous, just a few seconds ago. Now, these lines, they correspond to the frequencies of the light in which the emission spectrum of the elements within the substance are absorbing. Right? So if it absorbs certain wavelengths, those are the ones which you will not see in your absorption spectrum. So that's like the fingerprint of our substance. Now, the second one, outline how this spectrum might be used to, might be experimentally observed. So the light from the Sun can be, for example, projected on a screen after passing through diffraction grating, or a prism, just like the experiment that we saw a while ago. So we can disperse that light into its components, its different wavelengths, and we can find out what is the substance just by analyzing what is missing. Okay, so a more numerical problem now. One of the wavelengths in the absorption spectrum of helium occurs at 588 nanometers. Remember, nanometers is 10 to the power of -9 meters. Now, show that the energy of a photon of wavelength 588 nanometers is 3.38 times 10 to the -19. So, if you look at your booklet, you should have an equation for energy. And if you combine your equation for energy with the wave equation, you will get hc over lambda, right? How did we get this? We used E equals hf. This is Planck's constant, and f equals c, right? The speed of light, lambda f, and yeah, there you go. So by replacing this here, we get that equation. So if we put the values in, because this is constant, speed of light is also constant, and the wavelength we're given. So if we put those numbers in, we will find 3.38 times 10 to the -19 joules. That's fairly easy. Now, the diagram below represents some of the energy levels of the helium atom. Use the information in the diagram to explain how absorption at 588 nanometers arise. So, since it's an absorption, the electron is actually being raised to a higher energy level, right? Now, this energy is already given in joules, so we won't have to convert, as we did in the previous lesson, to electron volts. We can just keep it as joules. But now, the point is, we need a difference of 3.38, right? Because everything here is in 10 to the -19 joules. So how can we get a difference of 3.38 in this graph? We need to find here two different layers that when we make the difference, it's going to give us this value. So what if I go, what if I go from this one to this one? I'm going from -5.8 to -2.42. So -2.42 minus 5.8. This is my change in energy, by the way. So yeah, that's it. So that's going to be 3.38. Now everything here is in 10 to the time negative 19 joules, 10 to the power of negative 19 negative joules. Now number 3, mark this transition on a copy of the energy level diagram below. What you would do is this, just draw an arrow, okay? Don't, yeah, that, done. Easy, isn't it?